Hi and welcome everyone to this live Q&A session around decarbonization with oil-free heat pump technology. I'm seeing that a lot of people are checking in here from all over the world, and that's really cool to see. We are running on multiple channels, so there'll be coming questions in from all over the world on different channels. And I'm super excited. First of all, because this is not some Teams background. This is actually real life. So I'm here in at our headquarters where we have installed this oil-free chiller. Today is the heat pump topic we'll be talking about, but this is just to give a demonstration of the technology, and it's actually running at the moment. And I am responsible for sector integration and working as a business process expert on a various of different topics. And together with me today, I have Drew Turner, also working on this topic. But Drew, maybe give a few words to yourself.
Yeah, thank you, Jonas. So Drew Turner, worked for Danfoss Sector Integration, been with the company for going on 7 years now. Always working in the oil-free segment of the business with the compressors and the other components fitting into those systems, and most recently on heat pumps, which is of course today's topic.
Yeah, and I really see a lot of I see people joining from Portugal, from Canada. It's really cool to see, and just say hi to all of you out there. But Drew, why don't you start with giving us a bit of an introduction, a high-level introduction to the topic of decarbonization and the oil-free heat pump technology. And
Absolutely.
I'll remind all of you you have the chance now to also ask questions while Drew he is giving this presentation.
Yeah, please ask questions at any time. Thank you, Jonas. So if everybody here, or most of the folks on this, are probably going to be familiar with the Turbocore compressor technology, but that's the main keystone technology, if you will, that governs the opportunity that we see for oil-free heat pumps. But that is tied to, of course, the trend that we see as well, both with district energy systems as well as standalone buildings, for heat pumps and the growth of heat pumps, and specifically oil-free technology as the optimized solution for the heat recovery applications within that opportunity. But the background on that keystone technology, it's actually been around for a long time now. I think most of the folks on this live stream are going to be familiar with that the Turbocore technology has been around since 1995. It was originally invented by a service contractor who was rebuilding compressors in the field, and a team of engineers who at the time determined that none of the centrifugal compressor technology that was in the market was optimal for the applications. And so they determined that they basically started with a clean sheet of paper and said, if we could make the perfect compressor, what would it look like? And so they said it needed to be oil-free, it needed to be extremely efficient, extremely small, and extremely quiet. And so based on those four main goals, they then backed into the technology choices that ended up being the Turbocore compressor. So since that time, the portfolio has expanded, and that's what you see here. So from that first invention and the first prototype compressor in 1995, the portfolio has significantly expanded to where we can cover a broader range. It's two main factors that it's expanded on. That includes on capacity and lift, and optimization of that lift. And lift corresponds with differential temperature and pressure. And so on those two factors, that's what we've expanded the portfolio based on. Most recently, in the last, and forgive me while I get the laser pointer out, in the last couple of years, we've expanded on that lift factor to incorporate what we call the high lift capability, or high differential temperature capability compressor. That's really enabled the capability to in turn get into heat pump applications and to bring the benefits of oil-free compressor technology to those applications as well. And that's the main topic, is what are those benefits? And that's what you see here. The number one factor which drove the goals, if you remember, the first goal that I mentioned was going oil free. And that was based on what you see on the top left-hand side of the screen here, that all of the existing systems that were in the market at the time had significant complication and componentry that was just based on managing oil and getting it back to the compressor, which is the only place that it's needed. And so that goal to eliminate all those components drove going oil free, which then drove the technology choices, as I mentioned. But that also drove going extremely efficient. So if you go oil free and you do it with centrifugal compression, and you incorporate a variable speed drive, which I haven't mentioned yet, is incorporated in every Turbocore compressor that goes into the market, built into the compressor design itself. That gives you an extremely efficient solution, along with the permanent magnet motor, which also gives you the small footprint, which was an original part of the goals as well. So that permanent magnet motor, two-stage centrifugal compression, variable speed compression, and oil-free operation combined to give you extremely efficient solution. And it also, and this is kind of a byproduct of those technology choices, but if you go oil-free and you do it based on going with centrifugal compression on the front end, and then permanent magnets as well as trim magnets or magnetic bearing based design, then you have no contact in the compression, either the front end or the back end. That the byproduct of that is that it's extremely quiet. And so you'll hear this or not hear this based on where Jonas is standing right now with those units operating. And of course you can't hear them. And so that's a very good illustration of that lack of sound that's coming out of those units. But specifically what you hear or what you see with those units is that they're about 8 dB quieter than an equivalent capacity screw compressor, because the two primary noise generators coming out of a HVAC system, whether it's a chiller or a heat pump or a rooftop unit or whatever, the primary noise generator is the compressors, and the primary noise generator coming from the compressors is the metal-to-metal contact. If you go oil-free, then you have the best way to do that is with no metal-to-metal contact, and the byproduct of that is the extremely low sound. And then all of that also going oil-free results in a compressor design that is extremely low maintenance and a system design that is extremely low maintenance, which also improves the overall life cycle cost performance of a Turbocore based unit. The other benefit of the technology that he didn't recognize, and the team of engineers that created this technology at the time didn't really recognize, was that HVAC systems degrade in performance over time. And the two main factors that drive that same performance those two main factors that drive that performance degradation are those same that result in the lack of reliability with oil in the system. And then also the metal-to-metal contact that I mentioned was a primary noise generator. If you have neither one of those, which the Turbocore compressor and the oil-free system do not, then you shouldn't have any performance degradation over time or significant performance degradation over time. But that only matters if we can prove it. And so that's what we've been working to do over the last few years. Since Turbocore has been around for 25 years now, we have a good sample of existing units out there in the market, primarily on chiller applications. But what we did, or what we can do, is buy back 10-year-old compressors to retest them in the factory. So we test them before they go out the door, when they're produced, and then 10 years later when we buy them back. And then compare that performance to see how the compressor itself is performing in comparison to how it was when it was first produced. And what you see is a summary of that here. And that there's been almost no change in performance on average for each one of those compressors that we bought back. There's some measurement in here, which accounts for what you see on the plus side with the change in performance. But what we're ultimately trying to get to for the other Six Sigma nerds out there is a 32 sample size or similar, so that we can get that normal distribution to see what the average is. But what we're seeing so far from the samples is that it's almost none as far as average performance degradation.
Drew, let me
The
stop
other
you there.
factor that
Drew, let me stop you
Please
there
go
for a
ahead.
quick second. The questions are coming in, so I just wanna take one of them straight away. And maybe one of the comments I saw was also that you should please hide the share button, the share screen button in your
Oh yeah.
presentation.
Okay. Thanks.
So we have a question here from Muhammad Sarif. What oil-free compressor technology platforms are utilized in heat pumps? Could you touch a bit upon that at this moment?
Yeah, actually, that's a really good segue to this next slide. So, as I mentioned early in the presentation, there's two main factors that we've expanded the compressor portfolio based on. One of them is capacity. The second one is lift optimization. It's very critical if you're going to have a more efficient solution than the existing systems that are out there to have an optimized design to the conditions that it's going to operate in. And so that's the other factor that's driven that optimization is the lift optimization to the conditions. And for a heat pump, and to Mohammed's question, for a heat pump application, it really depends on the system design. And I'll show architecture examples later. But we've seen that depending on the heat pump system application, we'll generally use, it's almost never one. But we have three main optimizations of the compressor designs: a standard lift, which is used for water-cooled chillers primarily; a medium lift, which is kind of a hybrid for water-cooled chillers, less challenging air-cooled chillers, and then less challenging water-to-water heat pump applications, or low-stage water-to-water heat pump applications; and then the high lift, which enables the highest temperature operating maximum temperature point and the highest differential temperature. So from the low side to the high side. So to answer the question, it's all three that have come into play for the system architectures and performance models that we've put together for heat pump applications. Most commonly is the high lift, and then second is the medium lift, but in some cases we've actually used the standard lift. And I'll talk about the system application where that's the case in further on.
So actually, we have another question a bit related to this also, and this one is from Nick Arnejon, and he's asking, what is the recipe to set up a Turbocore chiller with 160 Fahrenheit or 70 C CLWT? Currently, suppliers are saying that it's about 140 Fahrenheit or 60 degrees C.
Yeah, the maximum that we can achieve today, it's a really good question because there's an evolution that's happening right now on that. So the maximum, you'll see it on the right-hand side here. The maximum that we can provide in discharge temperature today out of the compressor is 69 C. That in turn means about 67 degrees Celsius hot water temperature. But by the end of this year, the goal is to expand this on the discharge temperature side to about 77, and on the hot water temperature side, corresponding with that, about 75 C. So the recipe, and it depends on the application. The source temperature, did he mention the source temperature of the heat recovery?
There's no source temperature.
Okay. All right. It really depends on the source temperature. Because, and actually, I'm going to jump ahead. If you have a low source temperature, and this is shown on the right-hand side here. Actually, I'm going to jump out and then jump back in. So this is showing the source water temperatures and the variations. For a low source water temperature, such as seawater or ambient air applications, generally your combination of compressor, or the recipe to his question, that you'll use for the final heat pump solution is very different from what you'll use for a higher source water temperature application, such as industrial flue gas or a district heating return out distributed in a system. And then you have the medium source temperatures. So low source temperatures end up going back to the source at about 2 degrees Celsius. medium about 10 degrees Celsius, 30 for the high temp. The most common that we see is the medium temp. But the architecture that you'll use for a low source water temperature example is much more complicated and is very different from what you'll use for a high temp source example.
Yeah.
But the related to that, and just to finish the rest of the story on that, you know, for every 1K that you're decreasing the lift that the overall heat pump plant has to do, you're improving the system efficiency by about 1.5%. So what we try to do is, of course, focus on the higher source water temperature applications, as well as the lower supply water temperature applications as the optimal for a payback of these systems.
And Nick, he followed up here and said that they were looking at 50 Fahrenheit.
50 Fahrenheit
degrees.
for the source.
Yeah.
Okay. So 50 Fahrenheit, that's going to be, yeah. It depends on the differential and the flow associated with it. But with 50, you're probably coming out about, 38 to 40 on the evaporator. So it's coming in at 50 degrees Fahrenheit, which is, what about 11 degrees Celsius? Yeah, so that's on the lower temperature source water side. So it's more similar to this example. So you're probably coming out around 2. And so 55 to 65 with 10 and 2. And I'm jumping ahead again. But the system architecture that we would use for that is probably something like this with a parallel series arrangement. And you'll use that parallel because of that lower source water temperature, and then series, and then potentially cascade series, which is another evolution of that architecture, depending on the supply water temperature that you're providing. What did he say on the supply water temperature? Forward heat?
No. He only mentioned that the source temperature on 50.
Oh,
50 degree
he
Fahrenheit.
did. He mentioned 70 degrees Celsius on the supply water, right?
Oh, yeah.
I think.
Let
Yeah.
me just double check. Yeah, 7 degree, 70 degrees C. Yeah, correct.
Yeah. So that architecture, and it was Nick. Nick, your architecture would probably look something like this, with the cascade parallel, and then series and series cascade arrangement.
All right. And we have another question here, and I'll just, while Drew is asking this, I'll remind everyone to still just shoot any question that you have related to heat pumps or chillers or anything. Please send them across, and we'll do our best to answer them. We have a question here from Steve. And he's asking towards the lifespan of the compressor, and I think this came in around the discussion of the testing of the ones that we have bought back on the degradation of the compressor.
Okay, yeah, it's a good question. So Steve, thank you for that. The compressors are designed for a 20-year product life. And what we've seen is generally it should fit along those lines, even though we only been around and with a commercialized product for about 20 years. All indications so far are that they last about 20 years. So, or at least 20 years. If you're, and this is one of the kind of a corollary to this, one of the primary benefits with this technology is that if you're replacing something on these compressors, it's generally not breaking into they are semi-hermetic systems, so you can potentially break into them if you have to do maintenance. But generally, if you're replacing something, it's it's a electromechanical device overall, and that's part of the goal of the design. And so you're generally unplugging something and plugging something back in if you are replacing something.
Yeah. And we have a question here also from Enrique. Mugica, and he's asking to the Turbocore software. So he's asking specifically how can one download the software, but maybe you can also talk a bit more in general about the software.
Yeah, so the software is constantly evolving, and usually when you update the software, it's going to go through the OEM that ends up providing the chiller or the heat pump for the system. But the software that operates the Turbocore compressor is constantly evolving and is specific to both the compressor design itself as well as the refrigerant that's utilized in it. But it's constantly evolving to address any bugs that are in there, and then also to provide the latest in terms of operating parameters and then serviceability as well. But if you have an internet connection and you can and you have that connection with the OEM's software platform for the unit or the controller for the unit, then you can generally download the latest update, either on site or through their remote service tool.
All right. Okay. We have another question, and I really love seeing all of the questions coming in here. So please continue with them. We have a question here from Muhammad Jordi Abdul Razak. I'm sorry about my pronunciation. Have you ever compared the efficiency between a magnetic bearing system and the ceramic bearing system? And I think this was also ceramic. Sorry, yeah. And I think you also mentioned a bit about the two different technologies in the beginning.
Yeah, I would have to talk to our bearing guys whether or not they've looked at the losses associated with the ceramic bearing system. But I know that in general, a ceramic bearing system is going to have about the same performance as a roller element bearing system, right? Because all you're doing with the ceramic bearing based system is replacing the steel balls with ceramics, polishing up the raceway so that you can operate oil free, because that's the purpose of using ceramics, is to enable, or one of the main purposes, along with variable speed drive pitting, potentially, that comes with traditional steel bearings. But if you're going to replace them with ceramics, it's generally to go oil free. And if you do that, you're generally starting with steel balls. And I know that a magnetic bearing based system is just in terms of losses associated with that bearing system is more efficient than the traditional steel. So I believe that corresponds also with the ceramic. But if you look at from a product standpoint, what becomes most important is the comparison from the product standpoint. And the ceramic bearing oil-free solutions are very efficient, but the ceramic bearing-based oil-free system also adds a lot of complication to that system, because you have to lubricate that ceramic bearing-based system with liquid refrigerant as well.
Yeah. And I believe that was also one of the reasons for why the original inventor of Turbocor didn't go with the ceramic bearing system, right?
You remember the story well. Yeah, that is part of the story. It was part of his evaluation at the time. Yeah, he had the choice of magnetic, ceramic, and now what's evolving is, of course, gas, and that'll come about in the future as this technology pushes down into smaller capacities. But at the time, that was the choice, was really to go oil-free, either ceramic or magnetic. If you start out with steel ball and steel race, it's much easier to go ceramic. But he was starting with a clean sheet, and he determined at the time, and we still believe now, that the magnetic bearing is the best choice.
All right. So we have another question here, and please keep shooting them our way, from Muhammad Fahad. He's asking, what is the major parts using economizer in refrigeration process?
What is the major parts of the economizer in the? So you've got one example right behind you, there in the room, if you want to show them. So that, and Jonas is standing in front of, and do I get out of presentation mode to focus on you? Should I do
I think
that?
so, yeah.
Yeah, okay, I'll do that. So we can point it out, right? Okay. So, and I'm sorry, who asked that question again?
It was Mohammed.
Mohammed. Thanks for the question, Mohammed. So that right behind Jonas is a flash tank economizer system used on the NG chillers that are applied in the Danfoss headquarters building there in Nordberg. And so that's a flash tank economizer system. The answer your question, the components that are utilized in a flash tank economizer system are going to be somewhat different than the components that are utilized in a brazed plate heat exchanger economizer system. A brazed plate or microplate heat exchanger economizer system is a more compact system, but it has a little bit higher approach temperature, so the performance will be a little bit less. But the components that you see on there, you'll see that right on top of the flash tank. Jonas, if you want to point to the flash tank, yeah. Right on top of the flash tank, yeah, that's the Danfoss EXV and actuator on top of it for that economizer. And then to the right, you'll see the liquid level sensor, specifically the Danfoss AKS 4100 that's utilized as the liquid level sensor on that flash tank economizer system. Those are the primary components, and then of course you have the piping associated with it. Generally, the piping, the flash tank economizer goes back to the intermediate stage of the compression process after it's flashed off, and then the liquid, of course, the pure liquid, which is the purpose of the economizer, is distributed to the evaporator.
All right. So we have another question here from Gerd Verbomen. And Gerd is asking, is there a type of Turbocore compressor that works with natural refrigerant?
Not today. No, there isn't. So the primary refrigerants, and I've got a slide for that. The primary refrigerants that we use. Go ahead.
Yeah, and while Drew is finding the slide, I'll just remind everyone that please ask questions like Gerd and Mohammed did.
Okay, you can see my screen again.
Yeah.
Okay. So these are the refrigerants that we use today. So based on that question, this was Garrett that asked the question?
Correct.
Yeah, Garrett, thank you. The primary refrigerants that we use today on Turbocor or oil-free systems are both for heat pumps and chiller applications. You started out with 134A. That was the first refrigerant that was utilized. That was state of the art back when the technology was invented. Since that time, we've developed a portfolio with the lower GWP options, including 513A, 515B, and R1234ZE. Everything that we offer today is a synthetic solution, but the R1234ZE has, of course, the lowest GWP level, and also provides about a 3% efficiency benefit over top of the 134A refrigerant solution baseline. But just to mention as well, one of the main related factors to this technology, as well as other turbo compressor technology becoming more prevalent in the market, is refrigerants and the push down to lower GWP levels. If you're going to push down to lower GWP levels and at the same time minimize flammability, that in turn pushes you to lower density refrigerants. Lower density or larger molecule refrigerants in turn pushes you to technology which is optimized to remove a high volume of that large molecule refrigerant. That's turbo technology or dynamic compression in general. So we see the market moving more in this direction. Tying this back to the question, The primary refrigerant that fits into that low pressure category is 600A, which is isobutane, if I remember my refrigerants correctly, which if we wanted to do an isobutane refrigerant-based Turbocore compressor design, because we have the integrated power electronics in it, it is a significant modification to enable that, because otherwise that can be very hazardous, having power electronics in the refrigerant flow path with isobutane. So longer answer to your question, but today, no, we don't have any natural refrigerant solutions.
All right, thank you very much for that question, and please keep shooting them. I see that there are many coming in, and one of them here is from Jakob Rissler, and Jakob is asking, what are the primary heat recovery heat sources used for the heat pump systems that you have designed so far?
Yeah, that's a really good question. So I've got a couple slides for that as well. So the primary heat recovery heat sources that we've utilized for these systems, I kind of covered this earlier, but I'll show a few examples as the next step. So just to give, and there's a important story behind this as far as what drives our focus on these specific applications as well. But as I mentioned earlier, every 1.5, or excuse me, 1K that you can decrease the differential of work that the heat pump has to do equals about 1.5% efficiency improvement. So that in turn pushes you up in focus for the higher temperature heat recovery heat sources. But the primary, if you start with the lowest, is seawater and ambient air. And ambient air is, of course, higher variability. But the lowest temperature, of course, and the 6K or so that you get in terms of a loss with the air to refrigerant heat transfer pushes that down into the lower category, even on the warmer days. But then you have the medium temperature heat sources. And in general, these are what we call the symbiosis applications. And what I mean by symbiosis is the way we look at it, every chiller is a heat pump and every heat pump is a chiller. It's just how much you're lifting the temperature, or lifting the temperature in terms of the cooling provided and the heating provided, and whether or not you're making use of the heating and how you're making use of it. But in this category, most of these are those symbiosis applications where you're making use of both the cooling and the heating. And so for a district cooling application, you're using that district cooling return as the heat source. For a data center, you're cooling that data center and recovering the heat to, for example, a district heating system. It doesn't need to be a district heating system, but a proximity large heat load. And then wastewater. Wastewater is actually, if you look historically in Europe, and specifically at district energy systems, this is the most common application of heat recovery heat source for district heating. In this case, of course, you can't use that cooling, not very well anyway. But biogas slurry is kind of a related one, where you're actually making use of the cooling to provide more efficient natural fertilizer back to the farmers of those biogas plants, and then recovering the heat to the district heating. So just a few examples, and then to finish it off, industrial flue gas and district heating return, as opposed to district cooling return, is also a very good source for higher temp.
All right, and then we have a question here. So thank you very much for the previous question. I think we have a lot of good ones coming in. So thank you, Jakob, and James McBurney also had a question, and I think he was wondering a bit about. So we are in the room here at the Danfoss headquarters, where we are sort of playing with our own technology. So these two compressors, as you see, they are running at the moment. And James, he was asking, so why two compressors on this one? Is it to reach the tonnage needed? And what is actually the highest tonnage compressor that we have? So maybe talk to this about the system design and the tonnage that we can reach, or megawatt.
I'm gonna switch presentations for that. So from a capacity standpoint, it's a really good question because it also leads to one of the primary benefits of the technology. Just from the individual compressor standpoint, and this ties back also to the lift optimizations, but from an individual compressor standpoint, these are the portfolio of products that we have today. We have the, if you look at all the compressors in blue down below, these are the TTS and TTH series compressors, which generally fit into the category of about, in terms of kW, about 200 to about 700 kW. The higher lift capability optimized compressor designs are generally about 300 in the, with Turbocor in general, the number that follows the name of the compressor is the kW cooling capacity, nominal kW cooling capacity of that compressor design. So a TTS 700 is about 700 kW max design cooling capacity. TTS 400 is about 150, or excuse me, tons, but 400 kW cooling capacity. But those are the low lift optimized designs. For the higher lift heat pump designs, the primary ones utilized are the TTH 375, shown down here. And then the mirror, you'll notice that everything in green is roughly a mirror to everything down below that's in blue. These are the R1234ZE refrigerant-based designs, the TGS and the TGH series, also offered with 515B. But that same compressor, that higher lift compressor design, is the TGH 285. In terms of heating capacity, that's cooling capacity. In terms of heating capacity, each compressor is about 350 kW. But to the system design, and the one that Jonas is standing in front of, the reason that two compressors are used on that system, one of the primary benefits with Turbocor is that you can manifold as many of the compressors as you want on a single circuit. We've seen that same manufacturer who manufactured that chiller that's behind him also apply chillers with up to 12 compressors on them. So that in turn drives, and what enables that is the oil-free operation, because the main thing that drives separating compressors into circuits is making sure that you get oil back to the compressor that needs it. So if you don't have that limitation anymore, then you can manifold as many as you want. That in turn means that you can benefit from this heat recovery, or excuse me, heat exchanger scale and the approach temperature associated with the multiple compressors. And for example, running 2 of 12 compressors on that larger heat exchanger based system design. So, but in that case, there was 2 compressors used based on the capacity that was required. Over beside Jonas, there's also a single compressor unit. And we were just talking to the guy who's responsible for the design, who's Martin Brander, who's responsible for the Danfoss facilities and the oil-free systems, and working with the sector integration team now. He's responsible for that system design, and he specifically said that that was the single compressor based unit, and then the 2 compressor based unit. That separation was driven by just having some level of redundancy from a unit standpoint.
Yeah. Okay. Okay. Thank you. Thank you very much for that question. And I saw that there was also very positive feedback on it. So I think you hit the nail on the answer of that one. We also had another question from Mohammed Fahad here, and he's asking, in the refrigerator liquid receiver required between condenser and flow controlling device, how much refrigerant for that system?
So the liquid receiver. So the liquid receiver is going to be based on an air to water heat pump application and the reversing mode. And the funny thing about the oil-free systems, I guess a quick answer to your question is the oil-free reversing air to water heat pump based system has not been commercialized by one of our OEMs yet. There are several that are working on it, and we definitely see it as a significant opportunity. But the actual volume of that liquid receiver designed for a reversing air-to-water heat pump application, I can't give you insight on that, but that is something I'll look into as a follow-up. Our colleague Leping is fantastic at answering that question. For answering that question.
So of course, behind me and Drew, there's a great team working on these different topics of sector integration, heat pumps, and so on. We have
the technical experts.
Yeah, exactly. We have another question about air as a refrigerant in vapor compression heat pumps. What are your thoughts on that?
It's a good question, and I'm going to jump back to the refrigerant slide if I can. So give me just a second. So I can't remember if we had air. Yeah, we got CO2 on here. So air as a refrigerant is a higher pressure refrigerant. It is potentially, CO2 based refrigerant based Turbocore compressor could be designed, but it's not going to be more efficient than the positive displacement alternative that you can use for it as well. So that's why what I was talking about earlier about us focusing on the lower density solutions for a turbo, variable speed, oil-free, multi-stage turbo-based compressor, or any turbo dynamic compressor device to be more efficient than a positive displacement. It really needs to operate with the lower pressure fluids. So we can do one, an air or CO2 based compressor design, but it is not going to be more efficient than the positive displacement alternative that you can do. So it's not likely that we will.
I think we're looking for the best option that we can do with our technology, and we actually have a very concrete question also here from Manish Tiwari, and Manish is asking what to do if the inlet guide vane opening is not okay. So what to do if the inlet guide vane is not opening?
Yeah, our service guys will have to help you on that. So if that's a real, and I'm sorry, who asked that question?
That's Manish Tiwari.
Okay. Manish, if you can send us an email and let us know specifically what the issue is. If it's locking up, there was a previous issue with some of our inlet guide vane actuators that most of those issues have been addressed either in the field or by the OEMs who build the chillers and heat pump systems with these. But if there's one still remaining out there that needs to be addressed, it's probably that actuator that needs to be replaced. And we have a service bulletin that governs that. So the OEM who built that unit and our service bulletin associated with that should be able to address the issue.
So thank you very much, Manish, and I think that counts for everyone here. Please ask your questions. I also saw another one in the chat about looking forward to receiving the slides. If you already know what questions that you have, then please ask them, and Drew and I will stay here until you have emptied all your questions. We have one right here from Emil Siubek. Emil is asking how much capacity load is the most efficient point for the 70% that you mentioned earlier?
For the 70%. Actually, he answered his own question, I think. So in general, he's touching on something that's an important topic, right? The least efficient point, put it in reverse from, I guess, the devil's advocate perspective, is the least efficient point with an oil-free or Turbocore based system is always this design COP. That the payback that you're going to get for an oil-free system, whether it's in a heat pump application or in a chiller application or whatever, is going to be based on the off design conditions. Part lift is more important than part load in terms of that performance, but part load is important. And in general, the optimal point where you're going to get the optimal efficiency of a Turbocore based design is at about 70% of the design efficiency of that compressor.
Yeah.
So I think you kind of had some insight there, mentioning the 70%, but that is roughly the optimal point.
All right. So I hope that answered your question, Emil. Otherwise, then please follow up in the chat. And I see many more questions coming in, and we're really enjoying it. There's another one here from Wade Tiso, and sorry about the pronunciation. So what brand? Oh, sorry. What is the brand of the heat pump oil-free chiller on the screen? So this particular one that that's behind me here. This one is a NG refrigeration chiller that we have installed here in our headquarters in the southern part of Denmark, and we're using our own building here to test our technology, and that's also why we have the air purger here behind me that we also test on the system. And we're actually building a small sandbox here around in our campus to test technology and some of the applications that Drew he mentioned earlier. So Drew, I don't know if you have any more to say about this particular chiller, or more in general what who we're working together with.
Yeah, Inge's a very close and long-term partner, and also has the most volume experience, I guess, with our compressors over the last many years. And they also we enjoy highlighting this unit, and it's great that Jonas is standing in front of it today, because it also highlights the fact that they're using multiple Danfoss components in the rest of the system. We already talked about the AKS 4100 liquid level sensors, 2 of which you see with the red caps on them back behind him, and then also, and the chat just popped up, but the expansion valve on the liquid, or excuse me, on the economizer as well, is also a Danfoss component. And I believe there's also an isolation valve on the right hand side that's a Danfoss component.
Yeah.
So Inge is also a fantastic partner for us as far as integrating the Danfoss components in, whether it's a chiller or a heat pump system, but that's the OEM.
Yeah, so thank you very much for that question. We have another one coming in here from Mohammed Fahad, sorry. How we can do the energy and the exergy analysis of the VFD compressor based on heat pump systems?
Come back to us on that. I think that's going to be too long of an answer for us to get into here. Send us an email. Let's see, where is that? That was Mohammed?
Yeah.
Yeah. Mohammed, please send us an email. We'll send you our contact information as a part of this session. Please come back to us, and we'll come back to you.
All right. So we have another question here from Daryl Saranat, who's asking, what are the design requirements to consider eliminating premature corrosion of air-cooled condenser coils? And he is also following up here that when applying the wet function of Kledex pre-cooler pads.
Yeah,
So.
that's I'll speak to, that's an area outside of our expertise, but based on previous chiller experience, I'll speak to what I know, Daryl. In general, with an adiabatic system design, what you want to try to prevent is carryover of the liquid to the from the pads to the coils, or use a solution that fully vaporizes to cool the air, which is the ultimate goal, prior to reaching the coils. There is also treatment solutions for the water, actually a Danfoss treatment solution or a related Danfoss business treatment solution, which can help prevent that. But the coil treatment as well is key to that. And so the coil treatment can come in the form of various coatings. I think the E-coat or complete coat, or there's various names for it, but the full coating of the fins to prevent that corrosion is really what's critical, as well as the frame. And if you're in an environment where it's corroding the coils, whether it's with an adiabatic pad or not, my experience is it's going to happen with that adiabatic pad or not. It just can be accelerated based on carryover from it. So treatment becomes very critical, both in the treatment of the coil itself, but also in the treatment of the water being used in it.
All right.
Hope that helped.
So yeah, if not, then reach out. Then we'll try to help you more on it. So we have another question here from Wei Tiso, and Wei is asking, what is the minimum PR we require required to run the compressor to have enough internal cooling of the compressor?
Yeah, that's a really good question because it leads to one of the more recent benefits of the technology. So you've probably seen that there's one of the primary applications of Turbocore technology from a chiller standpoint is in data center applications. And data center applications have had the phenomenon over the last 25 years of increasing the cooling temperatures significantly, about on average 25 K from the, when I first started in this industry, they were cooling at about 7 degrees Celsius, which is comfort cooling temperatures, which was designed for combined sensible and latent loads. If you're cooling only a sensible load, and specifically CPUs in a data center, you don't need to do that. And you can raise the temperature at least to, sensible cooling levels, normal sensible cooling load chilling levels, which is around 15 degrees Celsius. But data centers have figured out that CPUs actually can reliably operate at much higher. And the reason our technology has become so prevalent in those applications is because of the low lift or low differential temperature and pressure benefit of the operation of that technology. So an oiled system, and it ties back to the oil versus oil free. If in an oiled system, you have to have a certain amount of differential pressure and temperature to return the oil back to the compressor. If you have no oil, again, you don't have that limitation anymore. So you can lower down that differential from the heat rejection to the cooling on the low side and the heat rejection on the high side. You can lower down that pinch even more, and so therefore operate at much lower differential and much more efficiently. And so that's a longer answer to your question that, you don't need to, with the low lift solution, which enables the cooling or a pump assist cooling back to the power electronics, you can operate as low as a 1 or the equivalent discharge temperature to suction temperature pressure ratio.
Yeah. So I hope that answered the question, and it's definitely a really good one. So thank you very much. And we still have many questions coming in, and we might shift a bit now with the next question more towards district energy. And this question is from Fabian Land. And the question here is, how will oil-free compressors impact heating districts in terms of the installation time, working hours, and the dimensions?
It's a really good question. It's a kind of a loaded question. Hi, Fabian. There's a lot of benefit associated with the technology with district energy systems in comparison to the technology that has been most prevalent in district energy systems in the past. And what I mean by that is a majority of the heat pump systems that have been applied in district energy systems in Denmark as well as other markets in the past have been based on on-site built units. And those on-site built units have a very large refrigerant charge and take a very long time to install and commission and get operating. Based on our recent experience, the direct comparison on that same job was about, I think it was 2 months for the on-site built, and then 1 week, less than 1 week, for everything that Fabian mentions there in that question to install, start up, and commission the factory prepackaged unit. So it's a very critical benefit of this technology as opposed to those on-site built units.
I think that we can share in the chat here a bit more about this particular installation, and our colleagues will share that with the Ringsted link, and we'll definitely follow up on that. So I we are looking at a few more questions coming in, but I'll really encourage you to really take the opportunity now. We are live. We hear from Danfoss. I'm here from Danfoss Nobo, and Drew is in the US. So feel free to ask us any questions that you might have in regards to heat pumps and or oil-free technology. We have another one coming in here from Kasper Larsen that asks, can this technology be utilized for individual buildings? So what drives focus on district heating systems?
Yeah, it's a really good question as well. So absolutely, it can be used on individual buildings. We're focused on district energy systems for a few reasons. I'm actually going to show a slide for that. District energy systems and the European trend, I think a significant portion of our attendees are in Europe. Europe is absolutely doing the right thing by focusing on district energy systems and the growth of those as the solution to long-term decarbonization of heating, and integration of heat pumps into those district energy systems as a part of that. That's one of the reasons that we're focused on it, because we see the trend to district energy system, both what's happening today in Europe, as well as what's starting to happen in other regions as well. And the combination of district energy systems, district cooling and parallel district cooling and district heating systems, and playing off of each other as the long-term trend. And it also becomes the ultimate solution to the other trend that's happening, which is potentially going to give us a blowback in terms of the heat pump trend. And what I mean by that is the resiliency factor. If you're going to replace all these furnaces and boilers on individual residences and buildings with heat pumps, and you're going to do it with little air to water heat pumps, that electrical load on that local electrical grid, and as well as the financial burden on those individual houses, unless it's fully subsidized, is significant. And the risk associated with that demand side electrical load, if the wind's not blowing and the sun's not shining on the renewables, which ultimately is driving that trend to the heat pumps on the demand side, that risk on that disconnect, if you don't have sufficient storage in between, is significant. And how you address that risk is with a district energy system itself, because that has a built-in storage factor, and it also enables multiple other storage options. And then it also enables utilizing multiple heat sources, including those symbiosis applications, such as on a critical facility. If it's done on a critical facility, such as a data center or a hospital or an industrial production process, where you're cooling that load and then recovering the heat to the district heating system. And here's the critical aha, right? Is each one of those critical facilities has their own backup power systems as well. So if your storage isn't sufficient and you need to operate that backup power, then all of a sudden you're supplying heat to the district energy system in addition to the critical cooling to that critical facility. So that's a longer answer to the question, but that's why we're focused on district energy systems today, is because we see the growth of that along with the growth of the electrification of heating as a symbiosis relationship, to use that word too much today.
Yeah, so thank you very much for that question, and we really enjoy all of these very diverse questions, whether they're technical or more general or to the one or the other side. Then feel free to share it here in the chats. We're streaming on multiple channels, so just go for it, and we'll do our best to answer them either now or following up afterwards. And we have another question here from Nick Arnejon, and he's asking, will Danfoss continue to support field retrofits of existing screw chillers with Turbocore compressors. So the question is around, you know, the screw compressors that we're working with today, and the Turbocore compressors.
So the screw compressors, the quick answer to your question is yes. If you replace the whole unit, we'll retrofit it. The problem that you run into, and that was Nick, yeah, Nick, if and you're probably familiar with this, is that if there's any oil left in that system, then it tends to gum up the sensors associated with the magnetic bearings, and hinders the operation of the magnetic bearing and therefore the compressors, and causes downtime and potentially failures. So it's very critical for the system to be free of oil. So if you're going to retrofit Turbocore compressors onto an existing system, it is absolutely critical that that system be thoroughly cleaned of any oil. I think that answers the question.
So thank you very much, and I see also new people are joining, which is super exciting. So we're getting some completely new people on board with new questions. We have here from one question from Lancelot Sharp, who's asking what situation or situations do you need a refrigerant pump for in the compressor, in the Turbocore compressor? Any specific application or conditions?
Yeah, that's ties back to the low lift discussion earlier for data centers. If you're going to operate below, and of course, because I'm trying to, I can't remember the exact number, but if you're going to operate below a certain pressure ratio, you need to enable the refrigerant pump or incorporate a refrigerant pump to make sure that the power electronics gets the cooling that it needs. So again, we can operate down to a 1 pressure ratio, right? But you need to have that liquid pump in there to make sure that the power electronics gets the cooling.
Yeah. So I hope that answered the question. If you have any particular questions around the specific line, I'm sure that we will follow up afterwards. No worries. We have another question here from Todd Mabote Simbini, and I'm sorry if it's not the correct pronunciation. What is the maximum ambient temperature that oil-free compressors can be exposed to?
Yeah, that's a good question as well. In our applications manual covers that. We'll send you the applications manual. I don't want to get, I have a number that I remember from the applications manual, but I'm not sure it's the latest. But in general, just something to mention on that. I do want to, if it's going to be a high ambient application, a really high ambient application, either in an unconditioned equipment room or outside in an environment where it's, you know, on a rooftop in Riyadh or wherever it gets extremely hot, most of our OEMs will build the compressor into some type of enclosure, and it can be very it doesn't need to be a high-end enclosure, but it's a good idea to protect it. It's not absolutely critical, but it's and I think that's a part of our application manual is that recommendation. But I will come back to you with a very specific number on the latest from the application manual.
Yeah, so it's really good questions and also refreshing our own minds here. So we appreciate that. And we have one here from Mohammed Fahad. And that is a very particular question around mass flow ratio. So he's asking towards the mass flow ratio of R717 to R12 for the same load and the same temperature limits. What is the proportion to the order of system?
R717. Okay, that's not in the scope of this. I think the quick answer to that is I don't think we want to cover that in the scope of this webinar, but or excuse me, in this live stream. But we can definitely come back to you and answer that question. I was pulling up my refrigerant slider, and then I figured, no, I don't think we want to do that in this live stream. But we'll come back to you. answer the question.
Yeah. So we have another question here, and please, I see more and more questions also coming in, and new people joining. So please keep asking us questions. We have one here from Ab Hilash, and sorry here for the pronunciation. Can you briefly highlight the importance of oil-free compressors in data centers and then the data center industry, which has a high SHR and now focused on high chilled water temperature for energy savings? So maybe you can touch a bit upon this question, and then maybe talk also about what we see for data center applications.
Yeah, I actually I spoke at length about that about 15 minutes ago, but can definitely do it again. But just to cover it briefly again. So SHR is sensible heat ratio, and absolutely data centers. That's the trend, right? 25 years ago, data centers were designing around comfort cooling conditions like 7 degrees Celsius, which is based on latent load and dehumidifying air. You don't have to do that with primary sensible load, which is what a data center is, and where you're not using near as much ambient air unless you're primarily cooling based on ambient air. So that sensible heat ratio and the benefit of oil-free technology operating at the lower pressure ratios that we were talking about earlier, because you're not managing oil, because you don't have to maintain a certain differential temperature and pressure to return oil to the compressor, you can operate at that lower differential. That in turn means that you're going to have a much more efficient solution for a data center operating at those, what were formerly 7 degrees Celsius and are pushing up to 25 to even 30 degrees Celsius on cooling temperatures today, and even higher in the case of two-phase liquid cooling. So there's definitely a trend there, and right now that trend says our technology is the optimal. Ours, as well as other oil-free technology where you're not burdened with that oil return differential pressure, are the optimal solutions for the application.
Yeah, and in fact, it's one of the things that we're also working on here, and I'm here in Norborg at our headquarters today. So as you see, these chillers here behind me are running live, and not that far from here, we're gonna build our own data center where we're also gonna test things like this, and we will also utilize the waste heat from the data center that will help us decarbonize the entire campus here at our headquarters. Fabian Delgado, he has a question, and he's asking to what other components and related factors are critical in these heat pump systems? I think
Yeah,
besides the compressor. Yeah.
That's a really good question, and I'm going to highlight that on a slide. So give me just a second. Okay, let me know when my screen comes up again.
Yeah.
And this is also tied to the question earlier on why are we focused on district energy systems today? So hiding that and then advancing this. All right, so the optimal solution for an oil-free based heat pump system, and this can be true for individual buildings as well, but it's more common in district energy systems, is based on having a lower heating return water temperature. A lower heating return water temperature enables us to utilize the different optimized compressor technologies for that low stage and then the high stage. That in turn means a more efficient heat pump system. With the ultimate system shown on the next slide of the series counterflow, or the series counterflow cascade that I showed earlier as well. But how you enable, to answer the question, how you enable that lower district heating return water temperature is, this is the supply side. We're the supply side, right? Because we're supplying the heating to the district heating system. On the demand side, on the building side, and this is the exact same phenomenon that you see in cooling applications, going to, every chiller is a heat pump, every heat pump's a chiller, and getting that mindset is critical because the same factors apply on the heating as well as the cooling, especially as you electrify the heating. And that is specifically enabling the benefits of the variable speed drive that you're implementing on that heating system, on the hydronic system. How you enable that benefit. And what I mean by that is those hydronic systems were designed for three-way valve systems, which were in turn designed for constant speed pumping systems. If you apply a variable speed pumping system to a three-way valve-based demand-side system, then you're not going to get any of the benefit from that variable speed drive because you're just bypassing all the flow around that three-way valve and maintaining the same flow of the system. So implementing pressure-independent control valves, two-way valves, to throttle that flow associated with the demand-side load becomes very critical. Along with that, efficient heat transfer stations, as opposed to heat transfer stations in that district energy system that were applied 20 years ago. You know, same thing again on the cooling side. Those rooftop units or those air handling units or those fan coil units, I think is a better analogy, that were applied 20 or 30 years ago aren't very efficient at heat transfer anymore. Same thing with the district energy system and the heat transfer station. So that heat exchanger that's applied to these, along with the pressure independent control valves, are what enables that lower district heating return temperature. In turn, what enables a more efficient series counterflow or parallel series counterflow heat pump based system. I hope that answered the question.
Yeah, thank you. Thank you very much. And thank you for all of the questions. And I also see new people joining in. Kamal from Morocco. Hi, Kamal, and welcome to the live session here. You know, all of you feel free to ask questions. We have one more question here from Todd Marboden, Bod Simbini. What are the do nots on oil-free compressors? So if you could make a checklist and say, you know, this you should not do, what would that be, Drew?
I think a better way to don't apply oil in the system is the first thing. That goes to the retro question earlier. Do not focus on applications where you're only going to operate the chiller system, you know, 500 hours or less a year. Oil-free, Turbocore based, and Danfoss component based system is not in general going to be your best first cost solution. So focus on those energy intensive applications. I highlighted earlier the symbiosis applications, right? The data centers, the industrial processes, the hospitals, all of those are very high operating hour, high load systems. And that in turn is going to mean a payback for that oil-free heat pump or chiller-based system. Do not operate I guess respect the boundaries. You know, we're expanding on, and just tying it back to the heat pump systems. We're trying to expand the capability of the compressors to operating in higher temperature applications. You know, keeping in mind that you're going to lose about 1.5% efficiency with every 1K increase that you do on that differential temperature. But we're going to push, nevertheless, the maximum hot water temperature capability of these compressors up to around 75 C by the end of this year. But today, that limit is about 67 C. And going any higher than that, and this is, I guess, the critical parameter I'll highlight as far as a do not. As you go into the top of that centrifugal dome, operating dome, and just keep that in mind. But as you get into the top of that dome, your ability to turn up and turn down in terms of capacity is going to be somewhat limited. So as you push into that upper range of the temperature, and as we push up further temperature range, capabilities is going to be somewhat limited. So make sure that you design the product both in terms of the operating temperatures, the heating temperatures, as well, and all the capacity turn down requirements and the variations of those. Make sure that the technology solution that you work with us and our OEM partners on fits with the system requirements.
Okay, thank you very much. I hope that was clear. I want to thank everyone for joining the live session here. We'll slowly start to wind down with a last question here. So we have one that we can close on, and I know you touched a bit upon that, Drew, but maybe just touch upon it again and make a bit of a summary in your own words. So we have a question here from Lancelot Sharp, who's asking, what's the next in the portfolio in terms of compressor size, in terms of refrigerants? Is it larger or smaller compressors? Is it both? What new applications are you excited about? Maybe touch a bit upon that.
Yeah, that's a really good question, and I actually wasn't prepared ahead of time to answer that. Both is the quick answer. So we're going to expand to larger, or well, we already expanded to larger sizes, and that's the main expansion, the larger size. We're also expanding into smaller sizes, and we'll give you more details on that later. Other applications, we're focused on district energy and heat pump applications in general. But a year ago, the discussion was, do we focus on heat pumps and high temp, or do we focus on process cooling, refrigeration, and low temp? Because the development of our technology and the high lift compressor design enabled both and enabled an efficient solution for both. So it became a choice, and we just decided that heating and heat pumps was a better opportunity for us at the time. Also because Danfoss has such a presence in district energy systems and heating in general. But the next opportunity, definitely with the existing portfolio, is lower temperature applications. And when you bring in the lower temperature applications, you bring in refrigeration, you bring in thermal storage, which the same trend to heat pumps and district heating, all of that is tied together, and that's that macrotrend flowdown. I don't think I covered in this presentation, but we have a flowdown that talks about that everything is interlinked. The trend to electrification in heat pumps and energy storage and thermal storage and low temp thermal storage, all of these are interlinked. It all ties back to climate change and electrification and the disconnect on the demand and supply and demand side with the integration of more renewables and how you address that with the energy storage and thermal storage being the most cost-effective solution form of storage and will be for a long time. So that's a longer answer to your question, but the low temp opportunity is the next focus, is the shorter answer.
All right. I think with that, I think we'll close the live session here. I want to remind everyone that this has been recorded and will be shared, and we'll on all of these questions that you have had, and if you still have some that comes up in an hour or whenever, then feel free to reach out to you. We are here, and we'll also answer the questions that you might have. So with that, thank you to all of you.